So in today's lecture, we are going to go over some aspects of naming and structure relationships in the carbohydrates. Okay, that is nomenclature and structure relationships. Okay, so here what we are looking at is a fructose. A fructose is some people call it, and we will be looking when we convert the linear form to a circular form, how does that structure change in terms of its name. Okay, so we will also in the way learn how to make the structure change, and we will do that exercise again and again. So this is D-fructose. Okay, first thing you need to do, you need to turn it on 90 degree. That is, it was like this backbone, so you can see the backbone has turned 90 degree. You see everything else is same. CH2OH is this carbon number 1, so it will start with the numbering 1, 2, 3, 4, 5 and 6. Okay, so we have turned it, this is number 1 and this is number 6 carbon. So you can see the carbonyl, the OH groups, all of them have turned. So this OH was pointing left, now it is pointing up because of the turning. This OH was pointing right, this is pointing down, turning. This is OH pointing right, pointing down due to turning. This CH2OH is irrelevant, so that is there. Now let's say first thing we want to try, we want to form a 6-membered ring out of this. Okay, so this, let's see if we can get the numberings right. So we start with this carbon 1, 2, 3, 4, 5, 6. One more time, 1, 2, 3, 4, 5, 6. See if we can form a 6-membered ring. So to form a 6-membered ring, you remember you have to always involve this carbonyl, right? The carbonyl group you have to involve, so that carbonyl carbon has to be part of the 6-membered ring. Now, see if you count it, let's see how we can form the 6-membered rings, and you have to use one of the OH. So if you try, this is first carbon, 1, 2, 3, 4, 5 and 6. Okay, so this is one way of doing it, right? So let's just use a different color to look at the possibility. So this is 1, this carbon 2, 3, 4, 5 and 6. This is one possibility of forming 6-membered ring, that is you just connect it here, okay, which we have explored here. Let's see if there is any other possibility of forming a 6-membered ring. Okay, let's use a green color. This is 1, we always have to involve this. 2, okay, then we have 3, if we consider this 4, then this is 5. So 5-membered ring will be formed if you use this OH. If you use this OH, it will be 1, 2, 3, 4. 4-membered ring will be formed. So 6-membered ring can only be formed using this particular OH. Okay, so that is how we will do it. So let's erase the other possibilities and focus on this OH based possibilities here. So I'm removing the green ones. Okay, and that is that. So 1, 2, 3, 4, 5, 6 are 6-membered ring formation possibilities. Now what is happening, this OH, as you saw in the last one, has lone pairs. So this is going to attack here and form the hemiacetal. Okay, so this attacks here and forms a hemiacetal. You can see that is a 6-membered ring formation. So the tricky thing while doing this is that, because this is now forming we are drawing this like a planar structure, the OH groups on the other side, they are not really losing their orientation. See, the position 4 and 5 OH still pointing down, position 3 OH is still pointing up. Okay, now this is the glycosidic bond, glycosidic OH. Okay, so this now is it depends on where you want to put it, is really relative. This particular one is we are pointing down, but it can be pointing up also, so that really is not in your hand. But what is fixed here is the stereochemical orientation of position 4, position 5 and position 3. So they are really fixed. Position 1, no, it is not. Okay, so position 3, 4, 5 must be drawn correctly. Okay, now to put it to give it a name, so let's see which of these three is the right name. So it is a D-fructo because it starts with a D-fructose, right? So that is for sure. Now all of them has the D-fructo in name. Okay. Now let's see what is the right name for drawing this. Remember, alpha means down, right? So alpha OH means it is pointing down, and it's a 6-membered ring, so it's a pyranose. Okay, 5-membered rings are pyranose. So this particular one would be named as, because this is OH and this is alpha D fructopyranose. Okay, alpha D fructopyranose or fructopyranose, whichever way you want to tell it. Now let's see if we can form a 5-membered ring. So this is the way of forming 5-membered ring. So let's see which OH would be involved. So again I am using a different color to find out which OH is to be involved. Again this would be your first carbon always, because this is the carbonyl has to be involved. Then if you see this OH2, this would be 3, right? So this is not a feasibility. Okay, so 3-membered ring we are not looking at, we are looking at 5-membered ring. So this is not right. So now let's look at the next OH. 1, 2, 3, 4. So if you use this OH, this would form a 4-membered ring. So that is also not something that we want. So let's look at the next OH. 1, 2, 3, 4, 5. So there we go. So we have to use this OH for forming the 5-membered ring. Now to do that, as we discussed, we were rotating this particular bond to do what we call 3 interchange and bringing this OH to this position, this CH2OH to this position, and this H to this position. So OH has moved to this position, CH2OH has moved to this position, this is H. So this is just simply a bond rotation, which we call a 3 interchange. Okay. Now having brought to this OH here, so it still is a 5-membered ring. If you count 1, 2, 3, 4 and 5. 5 is still a 5-membered ring. So let's attack this O on this to connect. Okay, and this is your connection forming a 5-membered ring here. Now all other carbons, chiral carbons, their orientation will remain the same. So position number 3, OH is pointing up. Position number 3, OH is pointing up. Okay. In position number 4, OH is pointing down. Position number 4, OH is pointing down. Position number 5, CH2OH is pointing back. Position number 5, CH2OH is forming up. Okay. Now this forming a glycosidic bond, we don't know which way it will go. So this can be, this is this orientation we have done. If we could have done it this way also, and it would have been fine. Okay. So I just reverse the position number 1. Okay. Now what is the right name for this? So we want to call this particular one, this is pointing down, so we want to call this carbon alpha. Okay, and again, so it would be number 2 and number 3, so and then D fructo is the common for both of them, and it's a 5-membered ring, so it's a furanose. Okay, so it's a alpha D fructofuranose. Okay, so that is how we do it. So we'll do more of this exercise of this cyclarization. Okay, so you can so this is basically what we did here. So same thing is people are doing using models. Okay, so here people are simply drawing it up and doing this, but basically the way I showed you, you can use that. So now, one important question here is that what percentage of the glucose stays in cyclic and linear form at the room temperature in the solution and solid. So it is found that experimentally linear form of glucose only makes up less than 3% of the glucose in the water solution. The rest is 1 or 2 cyclic forms of the glucose. When is it one? It is one of this one. Okay, so it is this one being alpha, this one being beta. So this is one of the 2 models that are there. Okay. So solid form, there is no information available. So this is what we talk about, the solution form in water solution. Okay. So linear form is really very rare, like 3% only. Mostly it is circular form. Okay. One more point, you can see that this is a equilibrium, right? So you can see that each of these forms can go back to the open chain form and can transform into the alpha and beta. So the alpha and beta, they are really reversible, right? So they can go back to its linear form, do a bond rotation among itself and form the beta. That's all it takes, right? So if you do a bond rotation, this carbonyl will be pointing down. If you form a bond here, this will form a alpha. In this stage, if you form a bond here, this forms a beta. Okay, so that is that. So let's start something ourselves to understand what we just did. Okay. So this particular one, D-ribose, forming this particular structure, D-ribose to this structure, what do we want to call it? Okay, so if we see the OH pointing down, this would be alpha. Then it starts with a D-ribose, so it should be D-ribo. It's a 5-membered ring, so it should be a furanose. Okay, so that is that. So it's a alpha D-ribofuranose. Alpha D-ribofuranose. Okay. So again, this is already something we have discussed, and so in this, what we see here is that the D, we are calling the structures all of them as D because this is the last carbon here, last chiral carbon here. All of them, the OH is on the right side. Okay, so this all of them are D. So these are the 8 sugars that are present in the aldohexose series. So these are the aldohexoses. Okay, and we are calling them, these are the possible ones. Okay. So the way to, there is an easy way to represent this or remember this. So let's see what these are. So the allose is presented as D 0 0 0 0. Okay, so this particular carbon is constant for all of them, right? So because this is D. This is all of them are D. Okay, so this particular carbon, all of them are having the same configuration. What changes is the other 3 configuration, and this is the way to remember this. So allose 0 0 0 means all of them on the right side. For alkanes, it is 0 0 1, meaning the first carbon it is reversed and the other 2 are 0 0. Okay. For the glucose, the second carbon, it is 0 1 0, it is reversed. For CH2, for D-mannose, the first 2 are reversed, so it is called as 0 1 1. Okay. For the D-glucose, it is 1 0 0, that is first carbon is, the last carbon is reversed and the first 2 are as it is, and 1 0 1 and so on. Okay, so that is how one way of remembering this. Okay, 0 0 0 0 0 1 0 1 0 0 1 1 and so on. The second way of remembering this is this mnemonic. So we call this all altruists gladly make gum in gallon tanks. Okay, so this was made by, I think, L. Fisher. So basically what this means that, so first one is all allose, ultrose, glucose, make, mannose, gum, glucose, in, aldose, gallon, galactose, tanks, talose. Okay, so that is that. So if you remember what is the orientation, and then if you remember this order, this will help you remember what sugars are in what order. Okay, so these are the abbreviated names. Again, you'll be able to Google it. So if you want, you don't have to remember. But some basics ones, if you should remember, that is fructose, galactose, fructose, glucose, mannose, ribose, xylose. So these things are very common. You have to remember them. Okay. In their amine form, is called amines. GL, gluconic acid, gluconic acid, glucosamine, galactosamine, and so on. Okay. So some other sugar symbols that are very commonly used. Again, these things you don't have to remember. If you have a PowerPoint or this PowerPoint with you, you can use this to understand the code. Okay, so here what we have is that you can see the hexoses are present in the circles. Okay, so these are the circles. N-acetyl hexosamine is squares, so these are the squares. Okay, so hexosamines is the squares divided diagonally, that is right here. Okay, so and then you represent different sugars with the different colors. So galactose, it is yellow. Glucose, it is here. Okay, so N-acetyl glucosamine is here. N-glucosamine, it is here. Mannose is green, so this is mannose in its in the just mannose. This is N-acetyl mannose, and this is just mannose with amine. Okay, so that is that. Similarly, you can do it for fructose, glucose, and so on. Okay, you have other acidic sugars. This is new 5-HC and so on. Okay, so these symbols are present. So let's learn how to draw a 5-membered or 6-membered ring from the linear structure. Okay, and see if we can practice it a little bit more. Okay, so let's start with the glucose. Okay, so first thing how we learned, that is we want to make a 90-degree turn. Okay, so let's see, that would be, so I will use a black color for doing this. Okay, so this is how it's gonna be. Sorry. So first thing before we start, we want to number this for our convenience. 1, 2, 3, 4, 5, 6. Okay. So this is number 1. Okay, and this is number 2, OH. Okay, 2. So I'm just gonna draw the OH for some time saving. Number 3, number 4, OH pointing up. Number 5, OH pointing down. Number 6, CH2OH. Okay. Now we want to draw a furanose, that is a 5-membered ring. So let's count and see which OH will form a furanose here. We'll start with this one. 1, 2, 3. So this definitely won't do it. So let's start again. 1, 2, 3, 4. So this won't do it. So 1, 2, 3, 4, 5. Okay, one more time. 1, 2, 3, 4, 5. So this is the OH that will do this job. So we want to bring it to the terminal position. Okay, so let's do that. So sorry. So this OH we want to draw now. Okay, this H we want to draw. So we want to make a rotation at this bond and do a 3-membered interchange. Okay, so this H will come, this H will come here, this CH2OH will go there, and OH will go there. Okay, so just give me 1 second. Yeah, so let's go ahead and do it. So up until number 3 it will be unchanged. So OH, this is number 3, number 2, and carbonyl is added as it is. So OH, this OH, I think I made a small mistake here. I have done a clockwise rotation. I have to do it anti-clockwise. So we want the OH to bring here. Okay. Anyway, let's go ahead and do it. So OH I have brought here. This whole thing, let's call this CHOH, that is position number 5, and then we have a CH2OH right here, and then if you want to do the H, it has gone there. We have to do one more rotation. So we want to do one more rotation here, and this would be OH right here, OH right here, 2, 3, carbonyl, and the OH will go there at position number 4. This H, so this is what I'm talking about, this rotation. So the H will be pointing up and CHOH right here, CH2OH right here. Okay, so that is now ready to form the 5-membered ring. So 1, 2, 3, 4, 5. So let's use this to form the 5-membered ring, and this is what we're gonna get. So the H and the CHOH and the CH2OH pointing down. Okay, we have the O to form the CO. Okay, and there's a CHO here, and then we have the position 3 OH pointing down, position 2 OH pointing down, and that is connecting right here. Okay, position number 1, this is position number 1 again. Now if it is alpha, that means this OH when it forms, that should be pointing down. Okay, so that is the structure. So this is, you see, this is alpha pointing down, this is D, it has been a D originally, and it's a fewer nodes because it's a 1, 2, 3, 4, 5-membered ring. Okay, that's a fewer nodes. Okay, now let's try that for making a alpha D gluopyranose. Okay, so first thing, again we are drawing a 90-degree rotation. So, and we are drawing this chain right here. So C double bond O, that is number 1, there is a H here. Okay, then we have the OH pointing down, that is position number 2, OH pointing down, position number 3, 2, 3, this OH pointing up, that is position number 4, and this H and OH, number 5, OH and H and CH2OH right here. Okay, so that is the 5-membered ring, that is position number 6. Now, how we make a 6-membered ring? Here, you count 1, 2, 3, 4, 5, and 6. Okay, so if you use this O, this would form a 6-membered ring. So, likewise, you want to bring this here. Let's do a rotation. So this will go here, this will go here, and this will go here. So C, O, H, all other carbons will stay the same. OH here, H here, number 2, OH here, H here, number 3, H here and OH here, number 4, and H here, OH here, and CH2OH here, that is number 6. Oh, sorry, number 5, and this is number 6. So now, if you make this is make a 6-membered ring. Let's count again to build confidence. Position number 1, 2, 3, 4, 5, and 6. 6-membered ring. Okay. So if you go ahead and make this is how the 6-membered ring gonna look like. Okay. So this is this O. Let's draw it right here. Okay, this this O, sorry, my bad. Let's make the 6-membered ring right here. This O here, let's draw it right here. Okay, this is position number 1, 2, 3, 4, 5. Okay. Now position number 1, there is CHOH, so we want to draw it as an alpha. So alpha should be OH pointing down. Okay, so this is forming this and OH pointing down. This is the H at that position. The position number 2, this is OH here. Position number 3, OH pointing down. Position number 4, OH pointing up. And position number 5, CH2OH pointing up. Okay, so that is how you draw it. You can draw the hydrogens if you want to, but this is how you going to draw gluopyranose as a 6-membered ring. Okay, so if you want to draw this one like that, this is, you can let's draw it like this. Okay, this is your O, this is your O. Okay, this is position number 1, which has a H and OH pointing down because of alpha. This is, let's say, 2, 3, 4. So position number 2, OH pointing down. Okay. Position number 3, OH pointing down. Position number 4 has a CH2OH, CHOH and a OH. So that is like this. Okay. H and a CHOH and CH2OH, CHOH and CH2OH. Okay, so that is what is happening here. Okay, so that is how we are drawing a 6 number ring site here. Okay, so let's stop this for now, and we have put more of this. This is solved right here, and you can use this drawing to see the practice in an animated format. Okay, and that is that. So you can practice on this particular slide. So I have put six linear chain of carbohydrates on their cyclic form. So you have to find out which one belongs to which, and also write there pyranose names. Okay, so I will stop the presentation right here, and we'll move on to the next one.